All right, I'm going to do some solutions from the Chapter 2 review starting on page 50. I'm having some trouble with my recording. It was like the fourth time I had to do this. Here we go. This is going to be the one. So I'm starting on page, I don't know, 51 or something. Problem number 62. And they give us these two measurements, 7.42 and 7.56. We cannot say whether or not they're accurate because we just don't know. We don't know what we're measuring and what the actual size is. So accuracy, no. Precision, yes, because the two measurements are close to each other. They're only off by 2% from each other. So we don't know if they're accurate, but they're repeatable, they're consistent. Seems to be a precise measurement system. So precision, yes. Uh, 64% error should always be positive. They barely mention that in the chapter. You really have to hunt for it. And there's just in one little example problem they say that. So not a great book you got there. So here's just an example. If there's some 2 foot tall person and one person measures him, just looks at him and estimates, oh, a person's about 1.8 feet tall. That would be an error of 0.2 feet. And another person comes along and estimates the height of this person, just looks at them and said, oh, no, that guy's about like 2.2 feet tall. That is also an error of 0.2 feet, but we don't call it an error of positive 2 feet, even though it is kind of an overestimate. And we don't call the underestimate negative 2.2 feet of error. It's just called 0.2 feet of error. So when you turn that into a percent by dividing it by the accepted value, according to the formula, it's still a positive number. So in this case, it would be a 10% error, whether you over or underestimated. So anyway, just remember it's always positive. Significant, not significant. That's 4 significant digits. So number 67, both numbers have the same number of significant digits, 4. So the answer should have 4. And this in 68, this one only has 3, this one has 4. So the answer should have 3 significant digits. You can't have an answer that's more accurate than one of the numbers that produced it. 72 is a straightforward one, density. So you're going to break out your density equation. Density equals mass divided by volume, which simplifies to 1 gram per milliliter. And that probably is something you should know, that the density of water is 1 gram equals 1 milliliter, or 1 milliliter equals 1 gram. You should also know that 1 milliliter equals 1 cubic centimeter. I say you should know, but you need to know that 1 milliliter equals 1 cubic centimeter. Just for water. Just for water, 1 gram equals 1 milliliter. But for any liquid, now I'm getting confused here, 1 milliliter equals 1 cubic centimeter, because that's just volume to volume. But specifically for water, the mass of water, 1 gram of water, is the same as the volume of 1 milliliter. And of course, that's not just a coincidence, that's just the way the metric system was designed. They decided that water would be, the most common liquid on the planet, so they decided that would be the basis of the unit of, either grams or milliliters. Grams. Okay. So we'll jump to 74. Also a straightforward one. We're just going to break out our density equation again. But in this case, they're giving us the density. I guess I'll be conscious of the units. What is the volume? Of 8.1 grams. And so I can see my answer here is going to be in milliliters. If the question asks what's the volume in gallons or something, I'd have to do a second step of converting units. But here I'm just going to, I guess I'll cross multiply. Maybe I'll write these units here. These milliliters, when we cross multiplied and went up to that side. So the grams cancel, 8.1 divided by 2.7, final answer equals 3 milliliters. All right, I'm going to check out 75. So for scientific notation, I can only have one digit in front of the decimal place. So I'm going to have to move over 3 decimal places. And if this number gets smaller by 3 decimal places, this number has to get bigger. Like right now, there is no second number. I guess it's 1 or 10 to the 0. So this number got smaller, bigger. So this number has to get smaller. So that tells me I have to use -3, not +3. I moved the decimal over 3 places. So I know this has to be either a 3 or a -3. And I make that decision based on whether I want this thing to get bigger or smaller. And this thing always does the opposite of what this one does. So here we go again. The left number got bigger, so the right number has to get smaller. So I know it has to be -3. Let's do one more. This one I'll be moving the decimal place over twice. So the number will be getting bigger. So the base 10 portion is going to have to get smaller. I could always unconvert this and just make sure it turns back into the original number. It's easier to go from scientific back to a decimal, I think. I know this -2 means move the decimal place over twice. I can see that gets me back, so double check that's the right answer. This one, 1, 2, 3, 4, 5. The number is getting smaller, so I'll write the small version. It was 400,000, now it's 4.3, it got smaller. So if that gets smaller, this thing has to get bigger. So I need +5, not -5. I'm going to skip D. And these ones are easier. I'll just do C. This thing tells me to move the decimal place over 3 places. All right. All right, hey you guys, you need to get one of these 2 calculators to make this stuff easier. I'm looking at problem 77. And the rule is if you're adding or subtracting the base 10 portion, like in part A, 10 to the 6th, that's the base 10 portion, has to have the same exponent. In A, they do, 10 to the 6th and 10 to the 6th. So you can add those 2 numbers, 11.57 times 10 to the 6th, and then you have to convert that to scientific notation. But since you get calculators on your test, who cares how you do it? Just use your calculator, I guess. And these would be the best calculators to get. If you're in Algebra 2, you should probably get this one. If you're in Algebra 1 or Geometry, this one. They have similar functions, but this one has a couple bonus functions that are kind of cool for Algebra 2. But what they both have is, I don't know, you can see the screen has like multiple lines, and you can see it handles roots, handles fractions really well, and it handles scientific notation, which isn't that special. Lots of calculators handle scientific notation well. But this, if you happen to have this calculator, that's the scientific notation button. And this one's right there. All right. So I'm not going to maybe I'll do one of these things. I don't know, probably just use your calculator. So I'll do 78a, 4.8 times 2.0. I'll pretend I don't have that cool calculator. Times 2.0. So I'm going to group I should call these something, the regular numbers together, and I'm going to group the base 10 numbers together. 4.8 times 2.0 is 9.6. And then for the base 10 numbers, I add the exponents. And that's what you do for multiplication. And then I have to verify that there's only one digit in front of the decimal, which there is, so I don't have to do anything extra. I'll do E just for fun. Times 2.4. So I group the regular numbers, 8.4 times 2.4, 20.1816. And then I add the exponents from the base 10 numbers. 6 plus negative 3 is 3. This one needs to be adjusted, so it's 2.016. This number got smaller, went from 20 to 2, so that means this number has to get bigger to compensate. Since I'm here, I'll go up here and do G also. And this one's a little difficult because we're adding, subtracting, and we need these to match the base 10 exponents, and they don't. So I'll have to convert one into the other. So I will, I guess, randomly convert the second one into base 4. Minus. So I want this to be 4, so this number is going to get bigger, so the other number has to get smaller. So that tells me I need to move the decimal place to the left. And now I have matching exponents in the base 10 numbers, so I can add these, or subtract in this case. So that's 9.25 times 10 to the 4th. Some of these up before, so I'm going to fix these. I've put in a new table here in green on the right. This is actually the same table from your book, but I just added a couple of things and took some things out. We're going to interpret this table as, let's do kilometers. 1 kilometer is equal to 10 to the 3rd meters. 1 kilogram is equal to 10 to the 3rd grams. So if we wanted to convert this one into a conversion factor, it would depend on our problem whether we put kilograms in the top or the bottom. So I'll just write both versions. But the 1 is always going to go with the non-base unit, meaning in this case kilograms, where grams is the base unit, meaning not kilo, not centa, not milli, just grams. So I'll write both versions. So this line represents both of these two conversion factors. Notice the 1 doesn't always go in the denominator. The 1 always goes with the non-base unit. In this case, the non-base unit is the kilogram, and the base unit is grams. All right, I'm going to do some of these examples. Here we go, grams to kilograms. They're just asking for the conversion factor. So my cursor's messing up. There we go. So they're not asking us to actually convert anything, just to write the conversion factor. Grams to well, what do you know? Grams to kilograms. So in this case, I'm starting with grams, converting to kilograms. So whatever you're starting with is the thing you want to get rid of, which means that goes in the denominator. And the number you want to keep or switch into goes in the numerator. And we said our new rule is 1 goes with the non-base unit all the time whenever we're writing one of these conversion factors. And then we can use the table to read the number that goes with the base unit. 1 kilogram is definitely equal to 1,000 grams. So that looks right. All right, let's do one more. Kilograms to grams. Easy. So now we're starting with kilograms and converting to grams. So the thing we're starting with is the thing that needs to cancel out with our denominator. 1 always goes with the non-base unit, and then I'll use my table to get the coefficient. I don't know, that's not the right word. but the equivalent number of base unit. Millimeters to meters. I'm trying to get rid of millimeters, so that will go in the bottom. I'm trying to convert into meters, that'll go on the top. One will go with the non-base unit, and then I'll use the table to get the number for the top. So millimeters, 10 to the negative third. This one's just going to be the reverse of that. Since we're starting with meters, that will go in the bottom. We're trying to keep millimeters or switch into millimeters, that'll go on the top. One with the non-base unit, use the table to get the number for the base unit. Alright. So we're trying to get rid of milliliters and keep liters. One goes with the non-base unit, which is milliliters in this case. Use the table to get the number in front of the liters, so milli, there it is. That's my number. Getting rid of centimeters, converting to meters, 1 in front of the non-base unit. And I would plug that in my calculator. Trying to get rid of centimeters, keep meters. One goes with the non-base unit. Use the table for the number in front of the base unit. I would use my calculator. 4.37 times, depending on your calculator, if you're using one of these ones, you go 4.37 and then times, I guess I would hit 1 EE -2, and this EE means times 10 to the, this -2. Or you can just not use that EE button, of course, and just times 10 and then use the exponent. Same thing. Alright, these aren't going to change very much, so you can skip ahead or keep reading or maybe turn the speed up. But I'm going to do the rest of them. Kilograms to grams. I want to get rid of kilograms and keep grams. One goes in front of the non-base unit, which happens to be in the denominator this time, kilograms. I'll use the table, I'll look for a kilo. That's the number that goes in front of the grams. So then I would type that in my calculator. Which I guess this is just going to move the decimal place over 3 places. 1, 2, 3. I gotta write the units. So I'm not gonna do the calculator part. Right, almost wrote a 1 there. But that's not right. The 1 goes in front of the non-base unit. It's not always in the denominator. So I'll use my table to look up the number that goes in front of meters. And then in my calculator, I would type, I guess, divide by. Or maybe the divide looks like that. Or you can use the fraction button and make it look like that. Oops. So here I have 2 units I need to change, both the grams in the top and the milliliters in the bottom. So I want grams to be replaced with kilograms. So I won't worry about the milliliters for now, but if I'm trying to get rid of grams, that means this conversion factor has to have grams in the denominator, and I want kilograms. That will go in the numerator. 1 in front of the non-base unit. Table says 10 to the third goes in front of the base unit, and this will get rid of my grams and leave me with kilograms, so that's good. But now I need to get rid of the milliliters. If the milliliters is in the bottom and I want to get rid of it, that means I need to put milliliters in the top in my conversion factor. Let's see, I want liters. 1 still goes in front of the base unit. Use the table. Milli is 10 to the negative third. This will get rid of my milliliters. And all this can go in the calculator. You multiply all the tops together. Sometimes I call that multiplying across. But that sounds too much like cross multiplying. So we just want to multiply all the tops together. Kilograms. Then the denominators, could use your calculator, but that denominator is going to turn into 1. Liters. Alright, I want to do one other one, which I'm sure I did with you guys already, but so I'm going to make up my own problem. I want to convert 20 milliliters into deciliters. Oops. And what's different about this problem compared to all these ones is I'm going from a non-base unit to a non-base unit. If you scan all these, it's either we're going from the base to a non-base or vice versa, but each of these has a base unit in it. I guess these ones also. So I'm going to make one where it goes from non-base to non-base. For these, I'm going to do it in 2 steps. I'll convert into the base unit and then back into the new non-base unit. There we go. So 20 milliliters. I'm first going to convert it into liters. Go to my table, 10 to the negative third. And this will leave me with liters. Then I'll convert it from liters into deciliters. So I want to get rid of the liters and keep deciliters. And the 1 goes in front of the deciliters. I'll use my table. 10 to the negative 1. So now 2 steps have been completed. And I can just multiply across 20 times 10 to the negative third in the top. Oops. And just 10 to the negative 1 in the bottom. I have to remember to write my units. Deciliters, and, oh, it's just deciliters. Alright. So one other one that's missing is, which I don't know if your teacher will make you do this, but you should have memorized that 1 milliliter of volume is equal to 1 cubic centimeter of volume. So for example, if he said convert 20 milliliters into cubic centimeters, it would just be 20 cubic centimeters, but you could write it out if you want. This turns into a conversion factor. We're trying to get rid of milliliters, and we want to keep centimeters cubed, so it's 1 milliliter equals 1 cubic centimeter. Also, on your cheat sheet, there's a different version of this. This one's in milliliters and centimeters, but I can convert it. I don't want to say convert, but a similar conversion factor that you just should know is 1 liter equals 1 cubic meter. This is the same thing, just it's in a bigger unit. Instead of milliliters, it's liters. So if the problem was convert 20 liters into cubic meters, you'd have to use this. All right, that's it. Send me any questions. So heads up, I was calling meters a base unit, grams a base unit, I guess liters a base unit. Anything that didn't have deca and kilo in front of it was a base unit, which is mostly true. But according to your book, at least for weight, mass, gram is not the base unit. They say kilogram is the base unit. But for all the other ones, liter is the base unit, meter is the base unit. There's not a contradiction like that. I don't know why it's like that, but who knows? Maybe that'll come up on a test. Probably not. But you should know the term base unit. It's what's accepted as the standard unit in the metric system for each type of measurement. So for mass, kilogram; for distance, meter; and for volume, liter. And here's just another vocab word, derived unit. So I guess if you have, in this case, speed, it's a combination of two other units. So they call that a derived unit. Okay, just some vocab. You want to not lose those points on a test in case they come up. And in general, just know the vocab just in case your teacher likes to ask those kind of questions on your test. All right, let's do a couple of these percent error problems. So the formula is, I don't know, I guess it's measured. I should look it up. Ooh, okay, I'll look it up. Okay, the book defines percent error as error over accepted value, which is the real value, times 100. So what is error? Error is the difference between the measured and the actual value. So I think before I said if there's a guy that's 10 feet tall, he's actually 10 feet tall, but someone just looks at him and estimates his height to be 9 feet tall, then that person is off by 1 foot. So the error is 1 foot. And you might be asking yourself, is it supposed to be negative 1 foot because he undermeasured it? That makes sense, but we always just leave it positive. Error isn't positive or negative. So make sure you don't catch yourself writing negative error or negative percent error. It's always positive. So in this case, the known height is 10 feet. The estimated was 9 feet, so the error is 1 foot. So that if we convert that into a percent, it's 10% error. All right, let's do a couple of these examples. So they're saying we know that the length is 5.5, but we measured it to be 5.2. So the error is 0.3. Now just plug that in my calculator. So for this one, looks like it's 0% error. Zero divided by 5.5 is 0. So yeah, 0% error. So this one's an overestimate, where part A was an underestimate, but again, there's no sign, so they're both positive. In this case, I'll put 5.7 first, just to make it come out positive. But I don't have to, even if I put it backwards. You know, if I do it like this, my calculator is going to spit out a negative answer. And don't forget, this is 5.5. So I'm just going to turn it positive. In this case, my calculator would spit out negative 0.2 for the top. But I would just come along and turn it positive. All right, I'll do a couple of these also. So 20% error. It's the same kind of thing. The accepted value minus the measured value over the accepted value times 100. So it's 0.1 over 8.96 times 100. And check these out. Round each to 4 significant digits. Currently, this number has 6 significant digits. The 0 is between non-zero digits, so it's significant. So this is currently 6. So if we round it to 4 significant digits, it's going to be 431,800. So these are now significant, and these are not significant. You might ask your teacher, how could you round this number to 5 significant digits, since this significant digit is a 0? So it kind of looked the same. So you might ask your teacher, how can you express this as a significant digit? The only way I could think of is if you wrote it as a scientific notation. Like this is 4 significant digits in scientific notation. And this is 5 significant digits in scientific notation. But there's not a way to do that without scientific notation. So ask your teacher, it'll be fun. This 1 to 4 significant digits is 10230. No, that's not right. I'm gonna have to round up. It's 10240. Oops. Now if I put that 0.0 here, now it's back to 6 significant digits. I can't write that. Now it's down to 4. Use 4. This one currently has 5. So this one, all I have to do is round off that last digit. I can't just delete it, I have to round it. Okay, and this one, the zeros before the first number digit are not significant. But the ones after are. So these 2 zeros are significant. So this one has 1, 2, 3, 4, 5, 6, 7 significant digits right now. But I need to round it to just these 4. 0.00, 1, 2, 3, 4 significant digits. This one currently has 5 significant digits. We're going to round it to 4. I'm being sloppy. I need to write my units. A lot of teachers are going to mark you off if you don't write your units. All right, good luck.